Welcome to Data Science with EJD. In this video, our focus shifts to supervised learning. We've been talking about, I started with data science, and going forward, we saw that machine learning is one aspect of data science we can consider. And digging into machine learning, we discovered machine learning can be divided into three parts, namely supervised learning, unsupervised learning, and reinforcement learning. So what I want to do here is to introduce supervised learning, and after now we'll take the algorithms in supervised learning one after the other. So we're going to see supervised learning is basically divided into two parts. You have the classification algorithms and you have the regression algorithms. So we'll see that here, and then after now we'll take these algorithms one after the other, and we go gradually. Okay. So, introduction to supervised learning in data science with EJD. Of course, the playlist, if you click this again, it takes you straight to the playlist. Yeah, for now, we have 5 videos. I've talked about introduction to data science, introduction to machine learning, the second video. The third is machine learning pipeline in Python. The fourth is linear regression from scratch and is scikit-learn. This is more like a kind of a sneak peek into the things to expect in the future. I mean, as the videos grow. And then in the fifth video, I talked about how to deploy machine learning models. Because at the end of the day, after developing your model, you want to be able to use it for in a real setting. Okay. So from there, the agenda is to see what supervised learning is. So we'll be answering the question, what is supervised learning? Then we look at classification versus regression, just like I told you. Supervised learning can be generally classified into classification and regression, right? So we look at some core terminology. We look at supervised learning workflow. We look at common algorithms, evaluation metrics, challenges and best practices, setting up your environment, and next steps and resources. Okay. So, what is supervised learning, right? I mean, I think I've explained it in the fourth video, for instance, when I just did that sneak peek about linear regression. So again, here this is a deep dive into it. Supervised learning is a machine learning paradigm where a model is trained on a data set containing input-output pairs. So you have features and you have labels to learn a mapping from inputs to outputs. Now, this may look like a lot of grammar, but let's go on. Has to be clear, a lot of big English or something like that. So the goal is to predict accurate outputs for unseen inputs. That's the goal of supervised learning. We want to be able to predict accurate output from unseen inputs. Then the data requirement, we need labeled data sets, e.g., features with corresponding outcomes. Like I've given a very good example, like you want to see how someone grows given their nutrition, their environment, and their nutrition environment, and say genetics. Yeah. So some real world example of this will be of supervised learning will be things like predicting house prices. So if you want to predict house prices given certain input, certain variables, right? You want to also detect spam email detection. That's also a very good example of supervised learning. Now, in the first case, right, you are going to get a price for house, right, based on certain other values. But for spam email detection, you want to be able to classify the emails you get based on the way they sound or something like that. You want to be able to say, okay, this is a spam and this is not a spam, something like that. That's classification. Then diagnosing diseases, that falls under classification too, right? So you want to know the kind of disease it is based on the symptoms and based on the results of your check. Then estimating traffic flow. Of course, that should be some kind of regression thing. Then sentiment analysis of reviews. You have credit risk assessment. Those are some real world examples of supervised learning. So taking this deeper, let's look at classification versus regression. And since those are the two main things we talk about as far as supervised learning is concerned. So talking about classification, this helps you to predict discrete categories. You are classifying. You want to be able, so based on facial features, right? You want to be able to say this is a boy or this is a girl. That's the idea of classification. So you want to predict discrete categories, or but based on facial features, we want to see, oh, this person is 60-year-old or whatever. So that's the idea of classification. An example, like just gave ahead, is the idea of whether an email is a spam versus whether it is not a spam. All right. I mean, we all get all kinds of emails, and of course, we are so used to spam that once you see it, in fact, some of these email services have even helped us. They just put any email that looks like spam, they just throw it into that place. So even no emails that are not spam, right? Some of them even go into that spam folder. Once they look like they have some features of spam messages. So the output for classification will be class labels like zero and or one. Like if you say male is zero and female is one, for instance, and you have some facial features. Once you look at that, you can say, okay, the answer is zero. So once it's zero, you know it's male or female. Then you can do the same for dog and cat or things like that. So the output is usually a label categorizing something. Then for regression, right, this helps to predict continuous values like age, like price, like numeric values like that. An example of that would be house price prediction, just like we talked about in the previous slide. So you have in the outputs in the case of regression is usually real numbers, like you want to get the cost. So if you want to predict housing price, maybe you can end up getting like 250,000, depending on the location, depending on where whether it's close to the road or things like that. So down here we see some tasks and whether they are classification or regression tasks. So task one, we have predicting movie genre. Of course, that's classification. So maybe based on the maybe the what is it called now, the trailer or something like that. You want to say, oh, this is an action movie, this is a comedy and things like that. So forecasting stock prices, clearly that's regression. Identifying dog breeds, that's classification. Estimating crop yield, that's regression. Fraud detection, so you want to know if a transaction is a fraud transaction or not, that's classification. Predicting exam scores, that's regression. So if you're going to be getting a real number value at the end of the day, a continuous value at the end of the day, that's regression. If you're going to get a category at the end of the day, that is going to be classification. And those are the two core components of supervised learning. Okay, so let's talk about some core terminology. First of all, we're talking about features a lot. What are features? These are just input variables used for prediction, e.g., age, income, pixel values, and things like that. For instance, I keep using the idea of growth, right? So to predict growth, you need to know the genetics of the person. You need to know the environment the person grew up in. You also want to know the kind of diet the person has been on, right? So these other things, right, these are the features that determine that determine growth. So these other features, these three things are the features, right? Then we also have labels. So we have features and labels broadly. So features are inputs while labels are outputs, right? So in that case, in the case I just gave now, the label or the target output is the growth factor, right? So labels are target outputs to predict, e.g., you want to know if a mail is spam or not. You want to know house price. You want to know how so you want to know how to want to predict someone's growth, right? So that growth value that you end up getting at the day is the label, where the features are the genetics, the nutrition, and the environment. Of course, we also have the idea of model in this case, just like that snippet we had about linear regression. You saw the model there was linear regression model, right? So model is mathematical function mapping features to labels. So you want to map all these genetics, diet, and environment. You want to map it to growth. So what you need to do that mapping is a model, it's a mathematical function that maps features to labels, e.g., linear regression, decision tree, and so on and so forth. So basically, we're going to be dealing with a lot of these kind of models. Then before now, I think when we're talking about machine learning, we saw the idea of training stroke test split. So that's not new. So this is basically you dividing data set into training, that is model learning, and test, which is model evaluation. So your model learns from the training data set while it evaluates. So the model is evaluated with the test set, right? So you have a data set, so you divide, so you give the larger portion for model learning and you take the remainder for model evaluation. So typically you can do 80-20 or 70-30. That's typical. All along we've been doing 80-20, meaning that we use 80% of the data set for training, and we use 20% for testing the model, or we can do 70-30, and in some cases we do like 67-33, depending on the particular the kind of data set you're working with. Then we have something called instance, which is a single data point, like a row with features and a label. For instance, talking about the case of growth based on nutrition, based on genetics, based on environment. So an instance would be a particular situation where maybe you have a particular person, say you have Mr. XYZ, and then the growth factor is this, the nutrition value is this, the environmental factor is this, and of course the genetics is actually this. That would be an instance. So a single data point or row with features and a label, that is your instance. So you have the loss function too. The loss function measures prediction error. So it measures, the loss function is about measuring the difference between the reality and what you predict, right? So a very good example of loss function would be something like mean squared error for regression and so on and so forth. So that those are some core terminology as far as supervised learning, of course, that's machine learning by extension, is concerned. So let's look at the supervised learning workflow. It will be pretty much like what we have under machine learning too, but we are just trying to not leave anything to chance. Of course, the first thing is, this whole thing is based on data. And of course, if you're in the data for data roles, right? I feel that everybody should be able to handle Microsoft Excel. That's the least level. In fact, some people just stop with Microsoft Excel and they make all the money they make with Microsoft Excel because it can do a whole lot. So for Microsoft Excel, then you can begin to think about other things like maybe say Power BI or Tableau. So from there, so at that level, you are like a data analyst or something, and you can take it further. As a data analyst, you can now get into Python or R. There's this fight going on whether Python is better than R or R is better than Python. For me, I've embraced Python and I have peace. So, so you get to that level. So once you're beginning to get into Python, even if you're using it for data analysis, you're already knocking on the door of data science. So you begin to work with machine learning models and things like that. Okay. So data collection, you want to gather high quality labeled data from reliable sources. And from there, you want to be able to pre-process. I mean, if you look at my playlist on data analysis with Python, there I talked a lot. Using pandas, we can handle missing values. We can normalize and scale features and encode categorical variables. So a lot of scaling and normalizing will also come up here as we're talking about machine learning, because now you also have some functions in scikit-learn that can do this job too, apart from what we've seen in pandas. Then we have model selection. So you want to be able to choose the appropriate algorithm that maps your features to your label, right? So you want to choose an appropriate algorithm, e.g. linear regression, SVM. Linear regression is one of the most popular. That's why, I mean, if you're thinking about machine learning algorithm, the first thing that will most likely come to your mind is linear algorithm. And that's why my fourth video is a snippet on linear algorithm. I'm still going to talk about it again when I get to regression algorithms. But after this video, I'll be looking at classification algorithms in supervised learning. So they'll be dealing with classification at that point. So when we get to regression algorithms in supervised learning, I will start again with linear regression. Then we go on like that. Then for model training, you want to optimize model parameters using training data. So at some point, we'll look at some of these metrics and how we can fine tune. Then evaluation, you want to access performance on test data using metrics like accuracy or root mean squared error. Then you want to deploy. So in the last video, I talked about how to deploy machine learning models. So that can help a lot. Though, I mean, I don't have all the infrastructure for deployment, because in a regular industrial environment, you need things like you need cloud storage and all of these things, right? You need Docker and blah, blah. So for deployment, you want to be able to integrate the model you have made into applications for real world predictions. The monitoring is also important. You want to continuously monitor and update the model for performance drift. So in case your model is going off course or something like that, or maybe you now have a kind of data you're collecting that that makes the model to be upgraded or to be discarded altogether and a new model adopted, you want to monitor to be sure that is going on. So the best practice in this case, you want to avoid data leakage by keeping test data separate separate until final evaluation. So if you want for test data, you want to separate it from the training data to be sure that you don't have data leakage. All right. So let's look at some common algorithms. Just like I said, right? After now, I'll take classification algorithms. I'll take each of these things one after the other and deal with them. And then I'll go after that. I'll go on to regression algorithms and make one video for each algorithm like that. So for classification algorithms, you have logistic regression, decision trees, random forest, support vector machines, neural networks. There's also k nearest neighbor. In fact, the next video is going to be on k nearest neighbor, which is a classification algorithm. It's not stated here right now. So there are many more algorithms, right? So I'll take as many as possible. For regression algorithms, you have the most popular linear regression, followed by polynomial regression. We have ridge and lasso regression. These are particularly good for what is this word now? For regularization. Some models are overfit, can be model you can have model overfitting or model underfitting. So ridge and lasso regression are some of the things we can use to regularize these models, to apply penalty on the model to be sure we get something good enough. Then we have gradient boosting, e.g., we have XGBoost. That's one of the most popular. That's like about the most popular algorithm for gradient boosting. Then we also have neural networks under regression algorithms, right? So the note here is algorithm choice depends on data set size. So the kind of data set you have, the feature complexity. How complex is it? Are your features, right? And task type. What is the task type? Are you classifying? Are you regressing? So you want to look at this to determine the kind of algorithm you choose. So the key thing is to start simple. You can start with linear models like linear regression. That's why linear regression is usually the go-to place. So if it gives you what you want, fine. If it doesn't give you, you may want to now go ahead to polynomial regression or things. And if that doesn't work, you may want to consider some regularization. So start with simple models like linear models before trying complex models like neural networks. When you get to neural networks, you're already going into deep learning and all of that. So I'll see if we can go that far in this process, right? So we have evaluation metrics, right? For classification metrics, we're just classifying, right? So we need to know about accuracy. So you want to see, like maybe you have 100 images and you want to see are this dog, so how many of them are dog images and how many of them are cat images? So the accuracy of your prediction can be calculated as correct predictions divided by total predictions. Of course, that makes sense. That's probability of correctness, right? Something like that. That's how you measure your accuracy. You're going to see that as we talk about classification algorithms, starting from after this video. Then you also have precision. So the precision is about the true positive divided by true positive plus false positives. So sometimes it's more like what we have in statistics where you have type 1 error and type 2 error. Type 1 error I think is uh, accepting the wrong hypothesis. I think I get confused about this. Well, I know one of the errors is accepting the rejecting the right hypothesis and accepting the wrong hypothesis. Those are the two types of errors we have. So that plays a bit into the idea of true positives and false positives. So if you classify an image as a dog and it is a dog, actually that's a true positive. But if you classify an image as a dog and it is not a dog, that's a false positive, so to speak. So the precision in that case will be true positives all over, both true positives plus false positives. Then we have recall for classification metrics. You have recall where you have true positives all over true positives plus false negatives, right? So false negatives are, oh, you identify that this is not a dog, but it is actually a cat. That's a false negative. Then we have F1 score too for classification metrics, which you calculate as 2 times precision times recall, all over precision plus recall. That's a class. Those are some classification metrics: accuracy, precision, recall, and F1 score. Then we have regression metrics. Here we are dealing with a continuous number, a real number, right? Because you're going to get a numeric value. So here, if you get a numerical value under classification, it is at best a categorical value, not something not a number that you can make calculations with. It's just a classification in that case. So, but for regression metrics, right, we have mean squared error. I think we've seen it under the snippet for linear regression. So that's 1 over n summation from I equals 1 to n of the square of the departure between the observed value and the predicted value. Then we have root mean squared error, which is square root of the mean squared error, right? Then we have mean absolute error. So you see, mean squared error has square and everything, but mean absolute error is just the summation of the departure between the observed value and the departed value and the predicted value, all divided by n. So you see, the square is what makes the difference, basically, mean squared error and mean absolute error. Then you have R square score, another metric for regression metrics. So it's basically, so the R square score, um tells you the proportion of variance explained. So for instance, I think in the snippet we did for linear regression, right, we got an R squared score of 0.45. That tells you that only 45% of of the variance is explained, by the model. So in that case, that's why you want something higher, right? So then the tip here is you want to choose metrics based on the problem. So if you are doing classification problems, you want to go for accuracy, precision, recall, and F1 score. So you don't want to use all this for regression metrics. So if you are doing regression, you want to use mean squared error, root mean squared error, mean absolute value error, and R squared score. So choose metrics based on the problem for imbalanced data. So if you have imbalanced data sets, you want to avoid accuracy and use F1 score or AUC. So even for classification problems, right? So if you have imbalanced data sets, don't worry about accuracy. Just go for F1 score or AUC. So these are better suited for imbalanced data sets. Okay, so what are some challenges and best practices? So some common challenges, you have overfitting. I mean, I mentioned that briefly before now. So you have overfitting, model. So in this case now you have the model length noise instead of patterns. So overfitting, I think, happens a lot if you don't have sufficient data or something like that, or the model is not good enough for the amount of data you have. So when you have overfit model, the metrics they are too good to be true. Like maybe you get a perfect metric, right? That's probably due to overfitting. Then there's also underfitting where model is too simple to capture patterns. So if you use a linear model for something that has a quadratic or cubic pattern, you are going to have underfitting. And there's imbalance data, like you have skewed class distributions like that. So when data is imbalanced, that can be a challenge. Then when we have missing data, incomplete. Now the imbalanced data is about maybe there's no normal distribution of the data set, and that's why sometimes we have to do some scaling. We have to normalize data and all that. Then there can also be missing data. Incomplete data sets affect model performance. All right, so you may want to clean out the data or replace values depending on the situation you're working on. Then there's feature selection too. So for feature selection, maybe you have too many features. Those are too many inputs, right? You want to be able to narrow them down. And the process of doing this is feature selection. So you want to be sure that irrelevant features reduce, knowing that irrelevant features reduce accuracy, you want to select the features that really matter. One practice that can happen is you can do a kind of heat map of the numerical values, like you get the correlation values. So the ones that are, so for features that are strongly correlated, you can just, if three features are or four features are strongly correlated, you can drop three of them or two of them. So because I mean the two of them all of them behave the same way. So you can have less things to worry about. So you can get something more reliable. So for best practices, right, you want to use cross-validation to assess model robustness, and then you can also regularize the model, just like I said before, using L1 or L2 regularization. These are connected with lasso ridge and lasso regression. So these are regularization stuff we are going to see later. So you can use this to prevent overfitting. When you have overfitting, then regularization is one way to go. Then you can apply techniques like smooth for imbalanced data. I mean, smooth has a full meaning. I've forgotten. I think it's synthetic something like that. Then you can perform feature engineering to enhance model performance. So for feature engineering, you can create new features from the already existing features. You can bin some features, like you can encode features, right? Like you have all these hot encoding and all this kind of encoding that can help like that. Then setting up your environment, of course, you need to install Python. We've used Python a lot. If you've been following me from data analysis, in fact, from scientific computing with Python to data analysis with Python to SQL with Python, and now, so you already know you need to install Python. Um, and install Jupyter Notebook for interactive coding. Now, the easiest way to do this is just use Anaconda for all in one setup. So once you install an Anaconda, everything you need is there. There's Python, there's Jupyter Notebook, there's Jupyter Lab, there is a Spider, and many other things you may ever need. So it's like Anaconda is like a one-stop shop for all of these things. Then you need to install essential libraries like Panda, Scikit-learn, NumPy, Matplotlib. Optional, you can use virtual environments like Ven, V, or Conda. I mean, but I've not used any of these things. So, but of course, if you need to, depending on what you're setting, you have all of these things. So use Anaconda for all-in-one setup with pre-installed data science libraries. So, like I said, there's Python, there's Spider, and all of that. So, next steps and resources after now, you want to practice with data sets, which you can get freely on Kaggle or UC repository. Okay, I think is this clickable? Okay, it's not clickable. Oh, they are not clickable. All right. So you can go for Kaggle or use UCI repository. Then you can experiment with different algorithms and hyperparameters. So sometimes you don't know the best model. You have to keep trying to see the one that gives you the best results. Then you need to also explore advanced topics like ensemble methods and deep learning, right? I mean, we go as far as deep learning. Let's see how that goes. Then you can join data science communities on Kaggle on Reddit. So for scikit-learn documentation, I think this is clickable. So if you want to know more about scikit-learn, because one way to learn all these libraries is look at their documentation and take them one after the other. So this is scikit-learn documentation. You see, scikit-learn basically takes you through the whole process of classification and regression, which are under supervised learning, and then you have clustering and dimensionality reduction. I think these ones are under so unsupervised learning, maybe as well as model selection, pre-processing, and all of these things. So you have all this. So if you go step by step, you can, in fact, under scientific computing with Python, what I've done is I actually took each function in the library and I went through. I'm still on it, and I stopped at some point. I have to go back later, right? So like when I took NumPy, I took each aspect. I started taking them one after the other, and I was going through. Then I got to. I'm still on SciPy, so from there I saw things like I think linalg, that's linear for linear algebra. Then you have optimize for optimization and all of those things. So so one way to really master a library is to take the functions one after the other and do a thorough job on them. So the whole idea of classification I've been talking about since is something like this, and for regression, it's something like this. So very soon we'll go to unsupervised learning and we'll be talking about okay, like you see under classification, right? Gradient boosting, nearest neighbors, random forest, logistic regression, and so on and so forth. So for regression, we have gradient boosting, nearest neighbors. So you can see repetitions, but the approach is definitely different. So for regression and classification, they are totally different. So for clustering, you'll be talking about k-means, HDB scan, hierarchical clustering, and so on and so forth. For dimensionality reduction, of course, that's where you talk about PCA, feature selection, non-negative matrix factorization, and blah blah. Then model selection, you have grid search, and so on and so forth. So that's talking about scikit-learn. Then you can also look at Kaggle data sets and computation. So they have machine learning data sets and they have competitions there. So if you by the time you gain a lot of confidence, you can think of participating in these competitions. So you need to level up with the largest AI and machine learning community, which is Kaggle, right? So join over to 24 million machine learners to share, stress test, and stay up to date on the latest machine learning techniques and technologies. Discover a huge repository of community published models, data, and code for your next project. Okay, so still here, of course, my channel is there for you to explore. Like one thing this channel will do for you is you have a whole lot of playlists that can prepare you for data roles. Like, of course, you don't just jump to these things, right? You start with things like basic calculus, which is there. You can go for things like matrices. Okay, there's matrices. You have basic calculus. You have even mathematical induction can be of help sometimes. Set theory, scientific computing. Of course, you have vectors. Of course, very key probability statistics, sometimes linear programming, graph theory, game theory, sequences and series, and of course, so it's you need all of this foundation. Even numerical analysis can be useful, numerical optimization techniques, like that. So before you can now begin to delve into data analysis with Python, SQL with Python, and now data science like that. Okay, so my channel is there for you to help. Now I have this book, Hands-on Machine Learning. In fact, I had to order the book from Amazon. I have it. It's just not close by right now, but I mean, it's one of the. I think it's more like the Bible for machine learning. So if you have not heard about it, you need to know that if you want to be a machine learning person, that's like the like the most important textbook that I know so far for machine learning. So you want to think about that as much as possible. All right. So thanks for watching. Be sure to like, subscribe, and comment. Let me know if you have questions, feedback, or topic suggestions. Feel free to leave a comment below this video, either on Facebook or on YouTube. And you can always subscribe by just typing in youtube.com/ at ejdansu, or if you have this PDF, which you can easily download from Google Drive by following the link in the description. So you just click on it and then you can subscribe to the channel, right? So that's how that has been today. And with that, we come to the end of introduction to supervised learning. After now, I'll begin to take the algorithms one after the other. I think the first algorithm I'll be taking with KNN, that is K nearest neighbor for classification. So I'll take the classification algorithms first. Then after exhausting as many algorithms as possible, then I'll move on to the regression algorithms, starting with linear regression and so on. And we'll keep moving that way. Thank you for listening. If you have not subscribed, you are missing a lot. Subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share also so that more people can have access to this great content I have here. Till I come your way again, keep doing data right. Bye.